Hello again. This is Math 1120 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Projectile Motion and Such. And again, I encourage you to be an active learner while watching this video. So we're talking about the trajectory of a projectile. So a projectile moves in a vertical plane that contains the initial velocity vector v sub 0, which is shown here, and its trajectory depends only on the initial velocity vector and on the acceleration of gravity. And the acceleration of gravity is down, and that's going to be minus the number g, so it's going to be minus 9.8. And when you track that, it will be in the shape of a parabola, as we've seen before. Now, to solve these problems, we have a very important fact, and that is that if you take a red ball and a yellow ball and you release them at the same time, but you just drop the red ball and kick the yellow ball out, what you see is really an amazing fact. The horizontal and vertical motions are independent of each other. At any given time, both balls, the yellow and the red, have the same y position, velocity and acceleration, despite having different x positions and x velocities. Successive images are separated by equal time intervals. This picture was taken with a strobe light. So the acceleration vector in projectile motion then is only the acceleration due to gravity, and there is no acceleration in the x direction. We're assuming there is no air resistance here. That's a harder problem that we study in differential equations. A couple of notes then. Here g is defined as the magnitude of the acceleration due to gravity, and g as a number is 9.8 meters per second squared, but the acceleration in this problem is minus g. And the minus sign assumes that our coordinate system is one in which the positive y direction is straight upward. So the path looks like this. Again, it's a vector. We have components, and what's really happening in the y direction is it goes up and it goes down. And independently, we have, and what we're doing is we have the initial component of the y, initial velocity is going up. It goes slower and slower and slower, eventually stops, and then comes down. So that's the component of the initial velocity in the y direction. In the x direction, we're assuming that there is no air resistance, and so it moves at a constant velocity all the way along until it hits the ground. So this will help you determine when it hits the ground, but then once you know when it hits the ground, you know how far it has gone. So again, the horizontal and vertical motions are independent. In the vertical direction, a projectile behaves like a free-falling object. In the horizontal direction, it moves with a constant velocity, no acceleration. Now we use the same equations that we used before, but we use them in each direction. So here are three equations that we've used repeatedly in solving LSA 9 and LSA 10. And we have versions of these in the y directions as well. We solve them separately and bring them together in order to answer all the questions. So here's what we have. In the x direction, we have this going on. The velocity in the x direction is the x component of the velocity vector, and x is equal to x0 plus v0x times t. But the y direction is a little bit more complicated. We have the velocity in the y direction, that's the component of the initial velocity in the y direction, and that is going to be minus, so it's the initial velocity in the y direction, minus gt. And then y is equal to y0, the initial height, plus v0 y t minus 1/2 gt² . Now there are some notes. The y direction is going to be minus gt, and then y is equal to y0 the initial height, plus v0 y t minus 1/2 gt². Now there's some notes. The y direction is going to be minus gt, and then y is equal to y0 the initial height, plus v0 y t minus 1/2 gt². Now there's some notes. the initial velocity vector components are v0x and v0y in the x and y directions. Vx and vy represent the x and y coordinates of the velocity at a later time t. x0 and y0 represent the x and y components of the initial position of the object, and x and y represent the xy components of the position at a later time t. An example is worth 1,000 words, so let's look at this example. This is called a home run hit. So let's consider a projectile problem in which the initial velocity is specified in terms of a magnitude and an angle. So the initial velocity then is going to be 37 meters per second at an angle of 53.1 degrees. So you want to find the ball's position and the magnitude and direction of the velocity at time t equals 2. Find the time at which the ball reaches its highest point in flight, and find the height at that highest point, and find the horizontal range, the horizontal distance from the starting point to where the ball hits the ground. Okay, so let's begin with finding the ball's position and the magnitude and direction of the velocity when t equals 2. So first of all, we're going to take the velocity of 37 meters per second, and we're going to resolve it into its x and y components using the sines and cosines as we did before of 53.1. So this is the initial velocity in the x direction. This is the initial velocity in the y direction. Then to solve part A, we ignore the effects of the air. And again, that's an assumption, but we're doing that here. And we want to find x, y, vx, and vy at time when t equal 2. So here's what we know then. T is equal to 2. So x is equal to v0x, which we found up here to be 22.2 times 2. So the x coordinate is 44.4 meters at time t equal 2. And y is going to be, and again, we're assuming that this starts at the ground level. Now, in the low stakes assessment I posed later, we're not doing that, so make sure that you realize that I'm changing that as we're going forward. But here, since that's 0 plus, this is v0y in the y direction, and then that is t minus 1/2 gt squared. So I plug in all those numbers, and I find that this is the y coordinate at time t equal 2. Now, the components of x, of v sub x and v sub y in the velocity vector at time t are, well, this v sub x minus this is v sub x. It never changes, so v sub x is equal to v0x, and that's 22 meters per second. Vy, though, changes. It starts at 29.6 meters per second, but then gravity slows it down. And so what happens at t equal 2 is I get 10 meters per second. It's still going up. Okay, so now we continue because we still haven't answered part A. So the magnitude and direction of the velocity vector at time t equal 2 then are, so this is the magnitude, that's the square root of v sub x squared plus v sub y squared, square root of the whole thing, and it's 24.3. You should check these calculations. And the angle that is at that time is 24.2 degrees, because that's the inverse tangent of, and this is v sub y over v sub x. And again, the picture can help you see that. It starts out at 53 degrees, but then the angle gets lower and lower. In fact, the angle up here at the top is going to be 0. But that then answers all the questions asked in Part A. Now, reminding you about what Part B was, Part B says, find the time when the ball reaches its highest point of flight, and find the height at that point. So you see we're saying, when does it get to this point, and what is its height at that point? So, at the highest point in the ball's path, the vertical velocity component, Vy, is 0. This was one of the things we did in our other low-stakes assessments, so that's a common thread. when does it happen? We'll call that time t1, and then what we're going to say is that Vy is equal to, and that's going to be V in the y direction minus gt. We find that that is equal to this, and we set that equal to 0, and we solve, and we get 3.02 seconds. And then the height is given by this equation. Y is equal to y0 plus v0 yt plus 1/2 minus gt squared. And we take that 3.02, we substitute into that, and we find that the height is 44.7 meters. Part C, we're to find the horizontal range, the distance from the starting point to the point where the ball hits the ground. Well, we know how long the ball is airborne. It is airborne this long. We also know how fast it's going in the x direction, and in the x direction it's going 22.2 meters per second. So that means to find the range, we have to ask, when does the ball hit the ground? And that's when y is equal to 0. So we'll take this, y is equal to, the ball started at, we set that equal to 0, and it's going to be 29.6 meters per second times t2, that's what we're calling this time, plus 1/2 minus 9.8, and that is t2 whole squared. Now that's a quadratic equation in t, but you know how to solve these using the quadratic formula, or factoring. And so you get t2 is equal to 0. We reject that answer because that's right when the guy was hitting the ball. But t2 is equal to 6.04 seconds. So this is the answer that we're going to use. And we'll say, okay, so the range is going to be v0 x direction times t2. And the t2 is 6.04. And so it lands 134 meters. And we were asking how fast it was going, and Vy is going to be this, plus that times the 6.04, and so that's when it's hitting. That's the Vy, and Vx was as before, so the angle that it's going to hit is the same as the initial angle. Pretty cool, huh? The last topic in this chapter deals with relative motion, and motion is, of course, relative. So suppose you had a bicyclist who was sitting here watching a train go by, and the train was going this way at 3 meters per second, but a woman inside the train was also walking from one side of the corridor to the other at 1 meter a second. So what's really happening relative to this cyclist? Well, and I've drawn it a little bit differently, but well, not so much. So the train is going 3 meters per second, parallel to where the guy is, but then the woman is going 1 meter per second this way, so the net is going to be, use the Pythagorean theorem, is 3.2 meters per second, and the angle is going to be 18 degrees. So you see that is going to be the velocity relative to the cyclist there that the woman is moving. Again, we're going to talk about relative motion when we talk about Doppler effects in ultrasound. And here is our low-stakes assessment number 11. And we'll talk about this just a little bit on Thursday and probably establish a due date. I'm guessing it'll be due a week from Thursday. So it's about the longest home run. According to the Guinness Book of World Records, the longest home run ever measured was hit by Roy Dizzy Carlisle in a minor league game. The ball traveled 188 meters, which is the same thing as 318 feet, before landing on the ground outside the ballpark. Part A. Assuming the ball's initial velocity was 45 degrees above the horizontal, and ignoring air resistance, what did the initial speed of the ball need to be to produce such a home run if the ball was hit at a point 0.9 meters above the ground level? Now this means the guy didn't hit it off the ground. He was hitting it in the strike zone, so it was 3 feet above the ground level. That's important, and that's a little bit different than the problem that we did. Assume that the ground was perfectly flat. And then part B is, how far would the ball be above a fence, 3 meters, 10 feet in height, if the fence were 116 meters, 380 feet from home plate. A good problem for you, involving projectile motion. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all. In closing, for now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. This lecture is continued in lecture 11.1.